I want to welcome everyone to the webinar today. You are viewing the best practices for implementing global calibrations webinar. And my name is Melanie Scott. I'm the Director of Marketing Communications at KPM Analytics. Our speaker today for the webinar is Bob Schumann. I will turn it over to Bob and let him present today's topic.
All right, thank you, Melanie. So to start with, just to let everybody know, as Melanie said, I am Bob Schumann. A little history, I started my career with Pioneer Hybrid. It's a company outside of Des Moines, Iowa in the US. It's one of the world's largest plant breeding and biotech companies. It was purchased by DuPont. Now it operates under the name Corteva. I was there for almost 11 years, spent about 15 years with Foss in various roles. And in 2013, I joined Unity. It was then purchased by KPM Analytics. So I've had a number of different roles, starting in a lab as a research associate, various product management, development, marketing roles. And my current title is Director of Product Marketing with KPM Analytics. And here is my contact information. So I will also be listing this at the end of the presentation in case anybody has any comments or questions. So a quick note, we will have a Q&A at the end of the presentation. In your window, you should see a screen like this, and there's a Q&A button. I would encourage everybody to, as you get them, type in questions that you might have, and I will address them at the end of the presentation. So a quick note about KPM Analytics. KPM Analytics was formed in 2015, right at the end of the year. We're headquartered in Westboro, Mass, outside of Boston. Early in 2016, the brand started being added to KPM Analytics. So Unity was the first one. Process Sensors followed immediately after, and you can see the various brands that we've been adding since then, with our most recent one being iPro System from Italy, a vision inspection company. So we are a global leader in analytical instrumentation, and we specialize in the food, feed, industrial, and clinical markets. The map over on the right-hand side shows our corporate offices, manufacturing offices, and sales and support offices. But we also have over 200 distribution partners across the brands, and we're present in 100 countries. And we do have a new website that we've launched about a month ago. It is kpmanalytics.com. It shows all of our brands, and we are coalescing all of our product presentation and support on that website. So hope everybody can take a look. So for today's agenda today is we'll go into a quick definition of global calibrations, talk a little bit about calibration development, just to give a background. And then I want to talk a little bit about global versus a customer or local calibration. So I will go through a development and then a specific example of this. Talk a little bit about best practices and how to use global calibrations to optimize your analytical situation. And summarize some advantages and disadvantages of global calibrations, and I'll finish up with questions. So global calibration, this is my definition. This is just a quick definition, an informal definition. But I think of a global calibration as a mature calibration consisting of a large number of samples representing extensive sample variation for a particular product or group of products. So there are a couple of key things here. Number one of which is mature. This is a calibration that's been under development for a while. It's understood to be towards the end of its, completing its development. And it's a very complete and robust calibration. And large number of samples and extensive variation really goes together. And this is just, a feature of global calibrations, and we'll address that in the next couple of slides. But this is a working definition that I have for a global calibration. So to step back, I think pretty much everybody on this webinar understands what's an NIR calibration, but I want to make sure that we're all on the same page. So an NIR calibration is a mathematical model which relates raw spectroscopic information to a constituent of interest. So I've got a couple of things I say whenever I'm talking about near infrared, especially introducing near infrared or spectroscopy to somebody. Got a couple of just things I say all the time. And one of them that I say, one of my phrases is, nothing in the NIR analyzers knows what proteins are. So this is a little diagram of a scanning monochromator, but all NIR analyzers are doing somewhat similar things, just with various technologies, but we're using a light source. Somehow we're separating out the wavelengths so that we can quantify individual ones. We're interacting with the sample either in reflectance or transmission, and we're quantifying what we see afterwards. But what the instrument sees is something like this. This is a log of 1/r reflectance. So this is the reflectance of the sample at hundreds of data points across this near-infrared spectrum. So nothing here and nothing that the instrument sees per se understands what proteins are. So what the calibrations do is they allow the NIR analyzers to predict the constituents that we're interested on based on these mathematical relationships that are stored in the calibration model. So really, the NIR calibrations are the key to getting useful information from an NIR analyzer. There are a couple of good rules to remember, one of which is that NIR is a secondary method. Again, there's nothing in the analyzer that knows what protein, fat, fiber, any of the other constituents of interest are. So we're relying on this relationship to get our useful information. Another rule that I think is very good to remember is near infrared or spectroscopy in general is very good at interpolating, but it's not very good at extrapolating and can be dangerous. So it's very important that you are including in your model any variation that you expect to see in your samples. So how's an NIR calibration made? Again, I think a lot of you know this, or most of you know this, but very quickly, we scan samples on an analyzer and we collect the raw data. We collect the spectra. Those samples are sent out to the laboratory for reference analysis. I've got a little table over here, constituent 1, constituent 2. These can be compositional type parameters, moisture, protein, fat, fiber, NDF, ADF, whatever. They can even be properties such as digestibility or hardness. But whatever our constituent of interest, we send those samples out to the laboratory and we get the reference values back. And then we combine these two bits of data into our calibration software. And the calibration software uses mathematical regressions to create that relationship, that model. And it's a big fancy linear equation, but it's really just a y equals mx plus b with many coefficients. And we can use this model and apply it to raw data and get our y, or get our constituent of interest. So the samples are really the key to accurate and robust calibrations. It's making sure that we've got all of the sample variation that we expect to see in this spectra. We make the relationship, and then we're going to have a robust model. Well, how does that relate to a global calibration? Well, I'm going to use a little example here and go through a calibration process to demonstrate what the process might be for developing a global calibration. So here's my situation, a hypothetical situation. We've got a company that's producing fish meal, and this fish meal is sold based on protein and fat content. So the company just needs a rapid at-line evaluation of moisture, protein, and fat to control their cookers and their dryers to make sure they're optimizing their production, but also to ensure the quality of their final product as they're selling their final product based on guaranteed specs. So they've investigated and they've chosen near infrared as the method or technology of choice, and they've given this job to a QA chemist named Lori. So her job is to calibrate the instrument. So Lori reads up on this a little bit, and Lori starts her calibration process. So she knows that she needs to collect representative samples. Again, near infrared is good at interpolating, but not at extrapolating. So she goes out, she looks at the samples coming into her factory, she collects representative samples, she sends them to the lab, she puts them into a calibration model, and the calibration model works well. So this calibration works well for her defined population. I would consider this to be a local calibration. It's based on a very specific sample set. It's based on one instrument, one specific set of conditions. But it's working well for Lori right now. And in evaluating this calibration, she finds out that the calibration is approximately as accurate as the reference lab tests are, but it's much more repeatable. In other words, it's much more precise. And I just put this in there. This is a standard experience for most NIR calibrations and high quality instruments. It's just a function of the technology. A good NIR calibration on a high quality instrument is going to be roughly as accurate as the lab is and much more repeatable. It's a real benefit of near infrared. So Lori's happy about this. She's got a success. They put it into production. They're analyzing samples through the rest of the year, and she can see in the summer and the fall that the samples start not to fit. And in her validations, she's seeing a little bit of some outliers, and she's seeing some predictions that aren't working. She investigates and she realizes that the fish are gaining and losing weight. The fat content is changing across the season. She knows what she needs to do. She needs to collect more samples to represent this new variation across the season. She sends them out to the lab. She gets the reference values. She makes the model. The calibration performs well. So her updated calibration is working well in all seasons, okay? And this is actually, the story to this point is based on a real story that was used many years ago by John Shank at ISI Software. So this is a real story. So from that point on, Lori again has success, and the company is super happy. So they get another instrument and they move it up the coast to another location. She starts analyzing more samples, but these samples don't fit. So again, we've got more variation. We've got new species of fish. So Lori goes through the same process. She gets the new species of fish, but she's learned also. She realizes that these fish are going to change across the year just like the first ones did. So she's collected these new fish samples across several times in the year. She builds it in. Now she's got an updated calibration that works well for all fish types in all seasons. Okay, things are going great. Career is doing really well. And the fish meal company is doing well. So they purchase a couple of additional factories. And these are in different locations around the world. And now they're looking at completely different environments, different fish that are eating different feed sources, plants, water conditions, all sorts of things are different. So there's all sorts of new variability. Again, Lori knows what to do. She builds in all of this sample variation. She puts it into the calibration. So now she has an updated calibration that works well everywhere around the year and for all fish types. So at some point in this process, virtually all possible sample variation has been represented and explained in the calibration. So this company and Lori can be pretty confident that virtually any fish type from any time of the year, from any location should be represented in the calibration. And all of these unknowns that she analyzes should be well represented. And therefore she's got confidence in the results. Another thing happened was during this process, she's got spectra, raw data from many instruments, different sample preparation methods, different grinders, for example, various lamps that have been exchanged in these instruments, different laboratory environments, more humid, less humid, different temperatures. So all of this variation has very subtle, but some effect on the spectra. So all of that variation has been built into this calibration. So during the process of calibration, the regression is looking to minimize errors, and any variation that does not correlate with your constituent interest gets ignored. So Lori has taught the model to ignore all of this variation that does not relate to protein, fat, moisture, for example, and is really zeroed in on the information in these samples that are important to those constituents. So she's confident that analysis of any sample in this group is going to show a precise and accurate result. The results are going to be consistent over time, location, across instruments. This is now considered, I would consider this a global model. So this is just one example that I used for fish meal, but it applies to all sorts of different products, generally agricultural and commodity type products. So this has been going on for a while in this technology, and I've had several people ask me, well, is there a limit to the sample types that can be combined into one calibration? In fact, a while ago, 20, 25 years ago, there was speculation, could we end up with one global calibration for all samples? Can we model everything in? And in reality, there's a limit right now to how much we can explain with our current NIR instrumentation, the information we collect, and the calibration or chemometric algorithms we have. So extreme sample sets can create variations we can't explain right now. So they might be nonlinear, discontinuous, or other relationships that we can't explain. So there is a limit to what we can explain, and we cannot just combine anything we want to analyze into one calibration. However, we can combine them into logical groups based on gross similarity in sample types. And various companies, various calibration developers have different ways of doing this. But I'm going to discuss one in particular. So I got this table just from the source on the internet. So it looks at the proximate composition of cereal grains. So we've got 8 different cereals that are listed here and the proximate constituents across the top. You can see that they're very similar in their makeup. They've got roughly the same protein, fat, ash, fiber, carbohydrates. They're somewhat similar, even though they're the distinct products. Combining these products into a global calibration can create a very robust, stable, and accurate model. And this is a very logical grouping. So to a specific example, I'm hoping everybody has seen, but a couple of months ago, we announced that KPM and Aunir have entered into an agreement, a partnership, for their Aunir Ingot calibration database. And we did this for a number of reasons, but this is the premier provider of near-infrared calibrations. So it's the world's largest independent calibration database with over 500,000 samples included, over 4 million data points. So those samples type times the constituents involved. There are over 20 years of seasonal, geographic, and product variation included. So going back to my fish meal story, Aunir has put together the work over many years to collect, a very wide range of samples in these calibrations. They're organized into 6 main libraries: animal feed and ingredients, pet food, aqua feed, animal proteins, wet and dry forage. The constituents vary per group. The one I'm going to talk about is the animal feed and ingredients, and it's these parameters here, these proximate parameters here that are involved. Okay, so the Aunir calibrations that have been customized and optimized for Unity instruments are the ones I'm going to describe now. We did just put out a new calibration data sheet. It is on the new website. It's pictured here. If you want to follow the URL, kpmanalytics.com/XP, you will see the XP analyzers, and they're in the resources. It will list the calibration database. And I think Melanie has probably put the URL also for this PDF in the chat if you want to take a look. But what it does is
I put that in the chat, Bob. So it's
okay.
The direct link is in the chat. So if you just wanted to download it and go straight to that data sheet, it is available there.
Great, thank you. So this data sheet goes through the various libraries and it breaks out the product groups and the constituents that each one of them are set up to analyze and are included. So I'm going to zoom in on the cereals group because we've been talking about cereals. I'm hoping everybody can see this on your screen, but the cereals group is here in the feed ingredients. It includes barley, maize, oats, triticale, wheat, red wheat, sorghum, and rye. Those are the main product types that are included. And they're grouped together as a calibration group for some of the reasons that I just described. Well, one of the first questions we get when we talk about global calibrations is what is the performance? So this is the performance of that cereals group with the Aunir Calibrations. I've listed the constituents across the top. We've got moisture, 2 types of oil. We've got ether extraction and acid hydrolysis, protein, crude fiber, ash, starch, sugar, NDF, and ADF. So on the left-hand side, we've got some calibration parameters or statistics, number of samples, standard deviation of the reference set, a couple of statistics for the calibration, standard error of calibration, and the R-square. These are kind of fit statistics. Really, I think a better way to evaluate these are cross-validation. It approximates an independent validation set. So we've got a standard error of cross-validation and an R-square of the validation set. And if you look across this at the number of samples that are included, and you look at the statistics, you can see that we've got fantastic performance across all of these parameters. And if we pull, if we go into individuals, for example, fiber, we've got 2,500 samples that have been included. The standard deviation in the reference set is 2.3. Our error is 0.36. Our correlation is 0.91. So our error is going to approximate the lab error. And we can apply this calibration to all 8 of those products in that cereal product group and be assured that we're getting great performance and accuracy on all of these sample types. So this is an example, but very consistent with what happens when we combine similar products into global calibrations, collect our samples across different geographies, different time frames, and include a lot of sample variation into a global calibration. So how do we use this? And I think that can be a little confusing when you get this calibration. It covers all of these products. What's the best way to use a global NIR calibration? Well, these are our recommendations. These are generalities to start with here. The first thing we would say is install the global model as a single calibration in your routine analysis software. So that in our product, UScan, that would be the calibration method, so that that model is present only once in your software. Then create a separate product for each major product type within this group, each pointing towards that same calibration model. Next, validate each product's performance against your reference laboratory. And to do this, select random samples from your production which represent the sample variation you expect to see during your normal reference, during your normal analytical days. Pick a number of samples, for example, 10. Send these samples out to your reference lab, get the values back, and compare them to what the NIR with the calibration is showing you. And if necessary, adjust the bias. So this optimizes on a per product basis the results from this global model. And finally, strongly recommend that everybody implements an ongoing validation procedure. I like a rolling validation where you're picking 2, maybe 4 samples per month per product. You're sending it out to your reference lab, and you are looking, for example, at the last 6 months of results, and you are validating your results that you're getting from the NIR against your reference lab. Remember that the NIR is a secondary method. It's always good to touch base with your reference lab. So what does that look like in practice for a Unity product? Again, UScan is our routine analysis software. It's based on modular groups of settings. These groups or methods are reusable. So we've got one called a scan method. It's how you analyze the sample with things like cup type, scan settings, things like that. We've also got a calibration method, which holds the model, different settings like outlier limits. If you're doing a moisture correction to a different moisture basis, those are stored here. And then we group them into a product, and our rules are one scan method and one or more calibration method makes up a product. And that product includes things like the name, product limits if you're in a production and you want SPC charts or something like that. It's got slope, intercept, or bias adjustments, any naming conventions, reports, limbs, exports, all of those are available at a per product level, okay, to optimize at a per product level. So for a global calibration, it would look like this. Each product has a unique name, product limit, slope, intercept. All of these different settings are on a per product basis. But in the background, they're using the same calibration method and the same scan method. So here we've got barley, sorghum, you know, everybody can read these. Unique limits, unique biases if needed, unique product settings per product. But in the background, we've got these common methods. So number one, this is great to set up. It's very easy to set up and organize in the software, but it's also very nice to maintain going forward. Because if for some reason I decide that I want to analyze my samples differently, I can change the scan method and all of the products get updated automatically. But for the purposes of this webinar, if I get an updated calibration model, I can update that model once and all of my products are updated automatically. So it's a very easy and efficient way of managing your calibrations within your analytical system while preserving the ability to really optimize and dial them in on a per product basis. So there's no silver bullet. There are always advantages and disadvantages to anything in life or in an analytical situation. So I've put together this list of advantages and disadvantages that I see. So, you know, some advantages, very rapid startup and implementation of global models. They're virtually turnkey outside of the validation I just described, but they're ready to use when they arrive. It's a very cost-effective way of purchasing and using calibrations, especially across a wide range of product types. They give excellent, robust, and stable predictions. Even if your products change over time, if you've got dry years, wet years, whatever happens, the very nature of a global calibration means that you're going to get very stable predictions. Covers a wide range of product types. As I just described, it's very easy to implement and maintain a global calibration. You can dial these in and optimize them to your individual products to make sure you are getting the best results possible per product. And because of the variation that's been built in, you're going to get very consistent results across instruments, environments, and locations. Okay. Some of the disadvantages. If you happen to have samples that do not fit in a global calibration, which is rare, but it can happen, it can be difficult to update a global calibration due to the number of samples required. So typically you need a certain percentage. A rule of thumb might be 5 or 10% of new samples to really update a good calibration. So when you're dealing with thousands of samples, it can be difficult to update calibration if your samples happen not to fit. Now we have ways of dealing with this. We've got a patented method of dealing with calibrations called condense, which we can reduce the calibration set but maintain the variation. We can also break things into individual product calibrations if necessary. So there are ways to do this. Another disadvantage is you might have, or you will probably have, slight biases between the product types. And I don't know, this is really not a disadvantage, but I wanted to emphasize this. best practices of global calibrations is you should validate each product type that you are going to be analyzing. Make sure that they are dialed in and optimized properly. And the last one is, it might not work for proprietary or custom products. Global calibrations really have their sweet spot with commodities, global agricultural type products. So finishing off, a quick summary. Global calibrations provide reliable and accurate predictions for many product types. They are available for commodities, agricultural products, and things like compound animal feeds. They can be configured to optimize results from specific product types. And so you can really dial them in and make sure you're getting the best results from individual products. And they provide a robust and turnkey analytical solution for many applications. So that's what I had for my presentation. I would be very happy to answer any questions if there are any questions out there. Please use the chat window that is down there at the bottom of your webinar screen, and just type in any questions that you might have. All right, and I've got one, and it says, how does the accuracy of a global calibration, I guess, compare to a local calibration? In general, the accuracy for a global calibration and a local calibration are going to be very, very comparable. There are instances where you might get a slightly increased or better performance, better accuracy from a local calibration in a very small sample set. But in my opinion, that is outweighed by some of the negatives of a local calibration. If you've got a local calibration and your samples change for whatever reason, or you're trying to share this across multiple instruments and it's only been built on one instrument, even though our instruments are very tightly matched, there are always residual differences between instruments. A local calibration can work very well on a closed system, but it lacks that stability and the robustness that a global calibration has. And the other thing I didn't cover in this presentation, but when you think about the big picture of what we're doing, what we're all doing in our laboratory, there are so many other sources of variation that are in there. So you've got sampling. That's one of the biggest ones. Sampling is one of the most difficult challenges I think we always face. But we've got different environmental conditions. We've got different sample preparation conditions. We're packing our cups slightly different, all of that variation. The global models are going to be so much more resistant to this extraneous variation, which is really noise, than a local calibration is. So I think that there are some real benefits, that in many cases outweigh the local calibrations. Another question, do you send the presentation? Yes, as soon as I'm done here, we will discuss it, but yes, we will send out a copy of the presentation to everybody. Any more questions? All right, I think I'm going to be finished here, and with that,
Bob, let me interrupt for a moment. I see a couple of questions in my chat window.
Okay, I was looking at the Q&A. I'm sorry.
Yeah, I think they're coming in both places. So
okay, thank you, Melanie. Okay, are these offline files or check online? As some clients claim that I think it's a competitor offers online all updated calibrations. These are, our global calibrations are delivered as files. So they're delivered as encrypted files, so they are not connected to the internet. We could deliver them through our community networking if a customer wishes to do networking, but we do deliver them as offline files. And then they can be updated just through the normal process through UScan. Next question, how can you determine if a global calibration for a product group will fit the product we are using? You know, in our case, it is finished aquafeed. Okay, good question. One of the best indicators of this are the outliers. So one of the things that happened in the last 15, 20 years is that we developed various statistical methods for determining whether or not the sample that you're analyzing is represented or fits in the calibration. And we do this through various spectral outlier types. So one of the first ways that we look at this is we look to see how the spectra fit, because we take a spectra first perspective. If the spectra are different, and if the spectra are not represented in the calibration set, that means that your sample is not present in the calibration set. So we look for spectral outliers. So that's our primary way, that's our first method of determining whether or not it's going to fit. Another question, what is the minimum number of samples required to create a calibration? Well, I do not like this question because I understand I started in a lab and we had a budget and we could only spend a certain amount of money for our reference data. Really, with full spectrum instruments and PLS, I don't like to look at a calibration before I've got 40 samples. And that's just my personal preference. I think it's very dangerous to have too few samples in the calibration. But as you saw in my fish meal example, there's a sliding scale. Moving from a very local calibration where you've got a well-defined sample set and incorporating more and more variation, and to ultimately you get to a global set. So on the upper range, I've seen calibrations that have 12, 13, 15,000 samples or more, and they perform very, very well. Another question, does it need routine recalibration? Global models don't, and that's one of the really nice things about global models. We do update our models periodically, usually on an annual or sometimes even a little bit longer, but you reach kind of a critical mass with these global models. And that's one of the real features of a global model is you've been working at it for so long and you've incorporated so much variation that it's kind of that law of diminishing returns. So yes, we do update our calibrations, but really we've got the global models that we are delivering and working with Aunir right now are extremely stable and incorporate a lot of samples. We just try to add new samples periodically and make sure we're following new varieties, new hybrids, things like that are happening. Another question, is the list of Aunir Cals, is it full or are there some others? For example, amino acids. There are other options through Aunir and through AB Vista, our partner. So the calibrations that I've listed in the Aunir datasheet are just the ones that we deliver through the Ingot database. So if anybody is interested in amino acids, and if they are a customer, for example, of AB Vista, there are options to get amino acids for select product types. And you can just send me an email and I'd be happy to help with that. Can global calibration be applied on soybean byproducts? Okay, now this is a great question. I've worked quite a bit with different soy meal, soy processors throughout the time. The incoming ingredients, the raw beans, the whole beans, the ground beans, and the ground soy meal, we have fantastic calibrations for those that are very mature, that I'm going to trust more than a reference lab. But the individual byproducts that happen during soy processing or corn processing that are proprietary and specific to the individual companies, we do not have calibrations for those. So, in general, I mean, it depends on what the product is and how similar it is to the original soybean samples in soy meal. But in general, if you get to a very proprietary byproduct that went through a lot of processing, that's going to be a custom calibration. Be happy to help you on that. We've got software to do that, but that will not be covered by global models. One more. If I have a lot of flours, all based on wheat, and I need to adjust the calibration for each flour or not, for example, bakery flour, pastry flour, cookie flour, etc. In my experience, we have not with our flour calibrations. We've got a finished flour calibration that incorporates these various flour types, and it's very accurate, and it works very well. Now we do split out, for example, the byproducts, wheat mids, things like that. We do split that out into a separate calibration, and we do split out ground whole wheat. So that is also a separate calibration. But for finished flour, we don't. Now, to this person that asked this, I usually take the attitude that when I'm approaching an analytical problem like this, I try to keep them into a common group just because it makes it easier for me. But there are situations in these various plants where they want to keep them as separate products. So I've worked with plants that they've got different products, or they call them channels sometimes, for the different mills within the plant. So they'll have an A mill channel, and they'll have products underneath that B mill. And that's because they want to keep their data separate. So it's more of a logistical grouping from a data perspective rather than a model. And when it comes to the model itself, when you're doing your validation, make sure that each one of those product types is represented, bakery flour, pastry flour, and make sure that it's validating properly. If it is, I would keep them together. The last thing I would say to this customer, I'm sorry if I'm wandering a little bit, but if you are in a process control situation and you've got different targets, for example, different protein targets or different ash targets for these various flour types, I would put them into separate products so that you can use the product limit in the SPC charting. It'll just make it easier for your plant operators to interpret the data. Would a global calibration be able to measure a combination of flour types in one sample? In general, yes. And again, that goes to the real power of a global calibration. In all likelihood, it's been seen. In all likelihood, this is present in the calibration. So when you're looking at forage types, for example, splitting out the individual forage types, the individual grasses, the various forage, or the different ensiled materials. Now, a lot of times there's a blend between a certain hay time, a grass hay, a mixed hay, a legume hay. The legume hay is going to have weeds in it. So there's kind of a spectrum, and these global calibrations do a very good job of seeing all of that variation and making very reliable results from those kind of in-between sample types. All right, excellent questions. Thank you, Melanie, for pushing me over to the chat window. So
no problem.
Great questions. My contact information is on the screen. Feel free to reach out, or if you've got comments on the presentation, I'd love to hear it. I'll hand it back to Melanie.
Yeah, thank you everyone again for joining and listening in today. We have recorded this session, and we will send a link to that recording to you if you want to review it later or share it with anyone in your company. Also, we'll include the slides and that link to that calibration library that Bob mentioned during the presentation. Thank you.
All right, thanks everyone. Have a great day.